Hi, everyone. So as Roxana mentioned, I'll be giving today a bit of a networking perspective on systems for big data applications. And allow me to start with a bang. So yeah. At some point, it should have been working. It worked. Think about Gay Fawkes Night. It's all around, there are fireworks. What happens when there are fireworks? People are taking pictures, people are taking videos, and everything is being streamed. Where is it being streamed to? To the cloud, right? Everything is moving to the cloud. The world today is moving to the cloud. But can the cloud actually handle everything that is streamed to it from the world? And I'm not going to talk today about all the aspects of cloud computing. I'm going to focus on one aspect, and that's latency. And latency matters. If we are talking on a millisecond scale, then every millisecond is equal to about $100 million for high-frequency trading companies every year. If we are talking about face recognition, then if I'm using something like Google Glasses and I'm scanning a room and I'm taking a picture of the people in the room, then if I'm processing the picture locally, then I'll be spot on each of the faces. However, if the processing is done in the cloud, I might just miss the person. I might even miss some people completely. So that's on the millisecond level. But what happens on the microsecond level? So we've been studying the effect of latency on the microsecond level, and especially for applications running within the data center. Let's take a set of data center applications and study what is the effect of static latency on them. So that's basically, I have a client and a server, and I'm just now moving the client to be a bit further from the server. So to give you a number as a rule of thumb, every 100 meters are equal a microsecond. So we measured for a set of data center applications, their base performance. That's what is marked here as the optimum performance. And then we started to increase the static latency between the client and the servers. And you can see that for some applications, such as Spark ridge regression, even a millisecond didn't affect them. However, for other applications, once you start to increase the latency, you can start seeing a degradation in the performance. So you can see, for example, for a machine learning application, such as a linear regression running on Strad's framework, even 20 microseconds of a round trip time mean 5% performance degradation. You can see that for several applications, from DNS through Strad, through Memcached, which is a key value store application, it's enough to have an order of 150 microseconds to lose 50% of the performance. And that's significant. But what really matters? What should we fix? What are the elements that we should now focus on in our research in order to improve the performance? So let's look at what are the contributions to latency. And for that, we are focusing here on standard setups. So we studied the effect of a setup that has a client and a server, both of them running on Xeon E5 v4, running at 3.5 gigs. So that's a rather strong new machine. And we did the compositional analysis of the latency breakdown within the host, as well as within the network, as I'll show later. I will not get into all the gory details. If you are interested in them, we have a paper on that, and you are welcome to read that. But we basically did a breakdown of the latency within the user space and the network stack, PCI Express, the entire host, and so on. So for example, if I'm looking on the host, on the latency of sending a packet within the host and the time until it goes back out with nothing at the user space, or at least the minimum possible. You can see that the time that it takes the packets from the second it entered through the port until it goes back out is in the median 4.5 microseconds. And for the 99.9 percentile, that's 21 microseconds. And the tail, which is close to the 100 percentile, that's 45 microseconds. Now, think about a client and a server. We are talking twice these numbers. That means median of 9 microseconds, 99 percentile of 40 microseconds, and a tail that is in the order of 100 microseconds. And these are numbers that are on the order that I've shown in the previous slides that already affect the performance of big data applications. Additionally, it's interesting to look on what happens when you're using kernel bypass. So what happens when you bypass the kernel? Then the median latency is now less than a microsecond. We saved 3.5 microseconds. We can still see, though, that even here the tail is still in the order of microseconds, 5 microseconds. So what should we fix? What should we focus on? This graph shows the breakdown of latency between the different components that we measured. How much is contributed by the application, how much is contributed by the kernel, how much latency is contributed by PCI Express, how much time is contributed by reading the timestamp counter. And you can think about it as the 99.9 percentile being where we've been before, the median being where we are now, and the minimum being where we'll be within a couple of years. And it's interesting because you can see that if the 99th percentile is dominated by the application, then already today the median is about 40% dominated by the time in the kernel. And you can see that PCI Express is starting to take more and more time. So you can see that in the minimum, the effect of PCI Express is already about 20% of the latency. But it's also interesting to note that there is no silver bullet here. There is no single aspect that dominates everything. But you might be saying, well, but it's in the network, then we should use also faster network devices, we should use different network topologies and so on. And the effect of the network itself really varies according to your application. So it's very different whether you are just using a rack or whether you have a setup that is optimized for high-frequency trading, or whether you are a data center that has a spine that uses store-forward switches and the 100 gigabit links. Because in each of them, the contribution of the different components is different. You can see that in a single rack, about 60% of the latency is spent within the NIC and 40% on the switch. Whereas if you are looking in a FAT3 network, you'll see that the NIC is only 25% of the time, and most of the time is spent within the switching devices. But maybe the most interesting result here is this one. What happens in a big data center where you have fibers in the order of 100 meters and more, and in big data centers you sometimes have fibers that are a kilometer long. Because you can see that there suddenly about 20% of the latency is spent on the fiber. And that's bad because, at least for now, we can't beat the speed of light, right? So unless we come up with a solution that doesn't include traversing fibers for such a long time, we have a problem that we can't solve. So to summarize the latency breakdown, what is good, which is less than a microsecond, what is bad, which is between a microsecond and the order of 100 microseconds, which already significantly affected the performance of applications, and what is really ugly. So simple operations within the kernel or in the user space are good, as well as the PCI Express, which is about half a microsecond, and also traversing through a single switch, which is less than half a microsecond today. However, once we start going through the kernel, once you are looking at the latency between a client and a server, on the network topology that has multiple stages in it, or traversing long fibers, then we have a problem. All of these contribute the order of microseconds to 100 microseconds. Now, what's really ugly is what happens at the end of the tail. And there we can see latencies that are longer than 100 microseconds. And that's evident especially in user space and in VMs. So you might be saying, well, I have an event that is a millisecond long, but it happens only in the 99.999999 percentile. But if you aggregate it over an hour, you'll find out that you are actually wasting about 5% of your time there. So it's really ugly. It's really hard to handle these problems. But on the other hand, they have a significant effect. So what can we do? One aspect that we've been looking at is better measurement and monitoring tools. And for that, we have developed a tool that is called Energy, a network research gadget, which provides a flexible line rate, a network research tool. And it has two parts. The first part focuses on a faithful emulation of data center latency. Because I'm not Google, I'm not Amazon, I'm not Facebook, I don't have a big data center. But I still want to study how data centers behave and what is the effect of the data center, of the network in the data center on the performance. So what Energy allows us to do is to take measurements of latency within the data center and collapse them into the gadget here that we use, and to emulate the latency within the data center as it is seen by the server or the client. It also provides us the ability to implement not just constant latency, but also different latency distributions and to do rate control. So if, for example, we measure a set of latency distributions within different data centers, and that's something that each and every one of you can do today, we can then use this distribution within Energy and measure the effect of the latency distribution on the performance of different applications. So these are the same applications that I have shown in the first slide, but now instead of showing just the effect of static latency, I'm showing the effect of latency distributions. And you can see that some applications are still not affected almost at all, whereas others are significantly affected. But it's more than that, because you can see that the latency distribution affects the performance. So you can see that for different data centers, even if they have the same or rather close median latency, the distribution causes for some of them to have significantly different performance. And you can see that actually the latency that you can get in an optimal setting can be reduced by almost 80% in some of the data centers compared to the optimum again. What else can we do? Well, one of the most annoying parts when you are looking at a network is monitoring. You can read counters, but as data rate grows and grows, it means that you need to read and read and read more rapidly. You can also use all sorts of packet monitoring techniques like INT. But that means that you need to sync all the data and to process it. What Energy proposes is to do the pre-processing in the hardware so we can monitor different aspects such as the bandwidth or packet sizes, different statistics of the traffic that the device sees, and then provides not the counters, but a CDF or a PDF, the distribution of the results as a ready result. Now, another aspect here is the resolution of the measurement. Why can't I just use the software? Well, if I'm doing a measurement on the resolution of 10 milliseconds of different applications, you can see that if my link is 10 gigabit link, this seems to be rather underutilized. You can see that it seems like it takes only 2.5, 3 gig out of a 10 gig link capacity. And that's kind of lame. Your network isn't well utilized. However, what happens if I'm measuring the same traffic for the same applications, but with a resolution of 100 microseconds? That's what it looked like. So for Memcached, it looks about the same, but look at Apache and look on the machine learning application here. You can suddenly see that they are extremely bursty. You can see that you are reaching the 10 gig link capacity in bursts. So you can see that that's really, really different. If you have limited your network to be only 2 gig, it means that an application like Apache would have been limited significantly. The performance that you would have seen was significantly different. So it really matters. What is the resolution that you are using for measurement? And that's something that you can get only through using hardware infrastructure. So far I've mentioned a lot of terms. I said performance. We want to study the effect of the performance of the application and throughput and IPG and packet size and what is the frequency. People may think it has to do with TCP window size, inter-packet gap, so many aspects. So much that it's really, really, really confusing what really matters. And what we are trying to do today is to see how we can study from all this information that we can collect, that we can process, that we can look at real time, and understand for that how the performance is affected. How can the application behave better? So for example, if I'm looking on Memcached that is significantly affected by latency, I can now also see how the bandwidth is affected over time. I can see how packet size is affected, and you can see packet size distribution isn't affected. That's quite expected. But you can see also other aspects, such as the gap between packets and the size of bursts. And you can see that as latency, and that's static latency, each color represents a different static latency. As static latency varies, the size of bursts of packet, the number of packets in a burst is reduced as well. So you can see, you can start seeing here that different aspects of different applications have to do with the network. And we have such information for various applications, and we are studying how to leverage that in order to improve the performance. But there are also other solutions that don't have to do just with measurements. I have two use cases. I will go over the first one, and with a bit of luck, I'll have time to go over the second one as well. And the first one has to do with rethinking computing infrastructure. And that's kind of odd because today computing is not an infrastructure. We have a lot of types of infrastructure, whether that's electricity or sewage or railways or roads. And they all have a common denominator. And the common denominator is that they have varying scale. They are deployed on varying scales. So you can think about for junctions that we have the mini roundabout, and then the roundabout, and the box junction with the traffic lights, and then we have a simple interchange, and the bigger interchange, and the highly complex interchange. Well, in computing, we don't have that. We have the equivalent of the mini roundabout and the roundabout that's our mobile devices and servers, and then we have the equivalent of the highly complex interchange. That's the data center. But we don't have anything in between. And you might just say, yes, but we have all sorts of solutions. We have racks of servers, which is kind of like the box junction. Well, I don't want to drive into a box junction that is made from 40 mini roundabouts. Okay? But computing is still becoming akin to infrastructure. So what can we do? Well, Candy is computing as a networking device. And it focuses on the fact that we are currently streaming huge amounts of information into the servers, and the servers need to learn to cope with all this information better. So it puts at the core of the server a fabric device that then has all the other components around it. And that allows us to create a tiny data center, or rather a data center in a box, which pulls all the components of the data center into a server or a device that can serve as a scalable unit, okay? And it doesn't have to look like the drawing in the previous slide. It allows a flexible implementation of different types of architecture, whether they are looking at a centralized or a distributed network fabric, whether we like to have multiple memory controllers or centralized memory or a standard server architecture. And all of those have a shared aspect, and that's the fact that Candy is based on an interface agnostic fabric, which basically says, look, we are using serial interfaces. The fact that we are using serial interface for each and every one of those means that from the fabric device, it can interface different types of interfaces. Now, let's say that we have such scalable solutions, and these don't have to be just Candy. They can be also other solutions that will be presented later today in the server session. So we now can have a scalable infrastructure where a lot of information is aggregated from the home to a local compute node. And then the local compute nodes are aggregated into the edge compute into the aggregate compute, and so on in a scalable way. You can think about it like we have today the fiber to the home or fiber to the curb. Think about having the compute to the curb. And it means that it allows us to rethink also different applications, Exa-Scale applications. So think about an application that is driven by a lot of information from sensors, such as condition-based maintenance of different assets. So if you have a jet engine, and each jet engine collects a terabyte of information in every flight, and you are maintaining 1,000 of those, every day you collect a petabyte of data. Okay? That's already a big problem if you're trying to run a maintenance of that, and you are trying in the cloud to run a cyber replica of the assets model. And you are trying to analyze, is it likely to fail? Should I ship now a component to replace it? You can instead do pre-processing here in the Candy server and send only relevant information to the cloud, do the processing there, do the analytics there, and since you are applying your machine learning algorithms to it, you can say, wait, I don't need all the features from the source. I need just specific features, and provide feedback to the Candy server that will then send only relevant information. And this way, developing a closed-loop control over the system. Since the color isn't working.
No, it was. I put it to yellow amber earlier.
Okay, so it didn't. Okay. So
Yeah.
I'll skip the last use case, and I'm happy to discuss it later. So just let me summarize. Oh, sorry, the next one. Cloud computing isn't enough to us. Latency matters, and it matters because it affects the performance of applications. What we need is computing as an infrastructure that is scalable and calls for new server architectures, new hyper-distributed systems, and new tools for debug and monitoring. But there's still a long way ahead of us before we can get there. And if you are interested in more information, we have a bunch of papers that were already published on the matter, or just visit my webpage. All the papers are available there. They're all open. And I'd like to thank all the other people in the team that contributed to this work, and obviously our founders. And with that, I'm happy to take questions. And sorry for the delay.